Hello, everyone. My name is Chuck Cartledge. I am a person who likes to play with numbers, who likes to play with algorithms, who likes to play with little things. And in those little things, sometimes I find ideas, concepts, interactions that are just delightful. And this is one of them. I came across this idea of Kaprekar's constants probably in 2023, somewhere in there. And the claim for Kaprekar's constant is that you can take any four-digit number that has at least two different digits. So that means that a four-digit number like 1112 would be acceptable, whereas the four-digit number 1111 would not be acceptable. And the second one would not be acceptable because it only has one digit in it, really. The claim is that with any of these four-digit numbers, after a certain number of operations, really simple operations, you end up with the number 6174 forever. And the operations is only four lines long. So to me, that cried out for testing, for seeing if that in fact is true for all four-digit numbers. While exploring that idea, I bumped into graph theory, number theory, big data problems, just a whole realm and wealth of things from a little four-line algorithm, trivial algorithm. This is what that algorithm looks like. You take any four-digit number with at least two different digits. You split that number into its individual digits. You sort those digits from high to low and convert that sorted digits into a number so you can do a little bit of math on it. You say take those original four-digit numbers and you sort them low to high and convert it to a number. And then you subtract the big one from the little one. And you keep doing that until you reach the number 6174. Simple, really, really simple stuff. And buried in it is just a whole world of interesting things. And we're going to explore those things. We're going to use the language R because it happens to be one that I have, a language I have installed on this computer that I'm using now. And it's a language that lends itself to doing mathematical, statistical kinds of things. So let's pull up a application called RStudio. RStudio is a integrated development environment that is optimized for use with R. There are lots of IDEs. Some of them are tailored to specific languages. Others are more or less language agnostic. This one is RStudio. We're going to be using R. Specifically, the R that we'll be using is version 2024 10.13. I believe it's the most recent version as of today, but it's close enough. Over here on the right-hand side are a series of R files, most of which we'll be going through in the next little bit. Up here in the upper left are all of the are scripts that we will be looking at. We won't be going into much detail, into the gory details of the scripts, because this isn't a programming lesson. This is an exploration of Kaprekar's constant. And most of the stuff that we're going to be doing is language agnostic. Some of the big data stuff, whatever language you choose, may be easier or harder to do, but by that time you'll know what it is that you're trying to do. So let's get these things so we can look at them a little bit easier. Let's get rid of all this noise down here at the bottom and take a look at how Kaprekar's constant is computed in the classic sense, where we know in advance that we're going to be looking at for the number 6174. Every language is a reflection of the language originators, how they think about problems, what they do with things. How the language is used is a reflection of the individual, their training, their thought processes, and so on. And that's kind of how my stuff is written. There are things there are ways that I think about problems, and I kind of lay my code out that way. That's the way I do it. Got a couple functions up here at the top. And then we've got this main here that has some messy looking stuff. These things look really kind of messy. And then we have this loop right here that says, do this stuff until you hit 6174. And if we look at Kaprekar's algorithm, it says, give me a number, pad the thing with leading zeros if necessary, give me the digits. So that's what this thing does. This format is a way to get leading zeros, and the digits say, give me the individual digits from that number. That's what this function does. Then we sort them high to low. So we compute the minuend with the ordering digits. And ordering digits says sort the digits based on whether sort decreasing is true or false, paste them all together, and return the value as an integer. And we do that a couple times. We do it for the minuend, we do it for the subtrahend, and then we do a subtraction, and we repeat that until we hit 6174. Minuend, subtrahend, subtraction. We print some stuff out here so that we know, we can see how things are going. And then when we're finished, we say the program has ended. So now we have created a function over here and did some things to it, but we haven't run it yet. We're going to take one of the canonical values from Wikipedia that says, starting with the value 1549, run Kaprekar's routine. So we're going to do that. And what we're looking for is down here where the answers will be. So let's run this. And it stops. You notice we had the initial value of 1549. We split those digits out, sorted them high to low. So we got 9554, low to high, 1459. Did subtraction, sort, sort, subtract, sort, sort, subtract, and we got to 6174. And like a lot of examples in different scenarios, the example worked. All right, the example worked. Does this routine work if we give it a different value? Say our friend 1112. And in fact, it does. So if we go back and look at the initial claim, the claim was that any 4-digit number, assuming that there are 2 different digits in there, will terminate at 6174. Any 4-digit number leaves us about 10,000 different ways or different numbers to crank through there. That's a lot of fat fingering and doing things. That's where things like a computer program would come in handy. So Kaprekar's constant, classic, this kind of seems to work. But now let's take a look at the algorithm again. This is an idea that my advisor at Old Dominion University, Michael Nelson, pounded into my head about the idea of knobs. If we have an algorithm of some sort, a routine, a way of solving a problem that works, are there knobs on that routine that we can tweak, that we can twist to see how the routine works in a more general sense? We've got a couple knobs here that we're going to explore. The first one is what happens if we don't know 6174? How does this routine terminate? When does it end? How does this happen? How does this work or not work, depending on how you want to think about it, if we don't know 6174 in advance? Remember, this is an exploration. We don't know a lot of things in advance. We are wandering through this unknown space, playing, looking at things, trying to understand, trying to look at them. So what happens if we don't know 6174? How do we attack the problem? The way we attack it, well, 6174 in Kaprekar's world is an interesting number because once you reach it, you can never get to another number. If you take 6174, do the sorts, do the subtractions, you'll end up at 6174 again. You get stuck in a cycle. You can't get away from 6174. Well, let's try this without knowledge of 6174. We don't know about it. We do the same kind of things. We have a 4-digit number with 2 different digits. Only now we keep track of all the previous values that we've computed. We append the value to the list. We stick it on the end. And then we do our digits, sorting, subtraction, until we bump into the number that we've already bumped into a second time. So we're keeping a list of all of our answers, looking to find a repeat. Once we find a repeat, we're done. Let's take a look at that and see how that works. Let's clean this up so it's out of here. We'll go to this one where we don't know. We have the same basic functions. Get the digits, order the digits. And now we are keeping track of the previous values, all the previous computed values. We get the digits, order, subtract, print out what we're doing, and then if whatever number we just computed is in the previous values, we jump out and say we're finished. You'll notice at the top, line 1 is rm list equals ls function. That is a way to clean out anything that may have been left over from the previous iteration or operation in our studio. The thing to watch is if I execute just this first line, over here on the left, these things will go away. So let's take a look, let's do this, and they're gone. Again, that is just one of the things that I do because I do. So let's get everything set up. Let's run it. Now we have our functions over here. And let's do our 1549 a second time. These first 3 steps are the same as we had in the classic routine. Came up with 6174. This one, this step, we sorted the numbers, subtracted, and came up with 6174. And we stopped, which is kind of what we wanted to do. We are now exploring Kaprekar's constant without knowledge of 6174. For those of you who may or may not have suffered through one of my classes, my eternal adult beverage, let's see what happens with this routine. If we don't know 6174, excuse me, if we try a different initial number, our friend on 112. Goes through, terminates. If we then put this thing into a loop, where it checks it runs this routine for all 10,000 numbers and then keep track of how many operations it takes to get to this little loop at the end where 6174. If we do that, we'll find out that that number never gets greater than 8. Never happens. So if you want to impress your friends, confound your enemies, you can go down to some place where you can wager something and say, give me any 4-digit number with 2 different digits, and I will predict that within 9 iterations, you will end up at the number 6174. And then put a wager on. You'll win every time. So now we have this idea that we can take Kaprekar's constant, play with one of the knobs. In this case, take away the knowledge of that, of 6174. It is the same algorithm. It is the same way of doing things. Knowledge of 6174 is indirectly one of the knobs that we can play with. Kind of interesting. Another knob that we can play with is right here. 4. That is the width of the number that you start with, or the area that you are looking at. For 4-digit numbers, Kaprekar's constant is 6174. We've shown a couple examples of that. It takes a while to do them all. I'm not going to fat finger them in and do them. That's kind of something that you can do. But let's put a knob on this 4. Let's tweak that and see what happens. A prediction is that if we twist that down to say 3, obviously we can't get 6174 because that's wider than 3 digits. But is there a Kaprekar's constant for 3 digits? Let's clean this up. Let's go to width. Same type of things. We're going to do a bunch of cleanup on here, get our digits, order the digits. We've gone through those. Those are invariant. But now our main function takes 2 arguments. It takes an initial number, whatever that may happen to be, and a width thing. We've got our little messy stuff here, and we just do the same type of thing. So we keep track of all the previous values. We split the digits, we order the digits, we order the digits, we subtract. We say this is what we're doing, and we break it out. If we find the same number again, we break out and say the program has ended. All the same type of stuff that we have done in the previous ones. So let's go ahead and execute all that. And now let's start playing with it. Our friend, 1549, that's a width of 4. This is classic Kaprekar's constant. This is one that should end up with 6174. And it does. So we have some confidence that that width knob seems to be working. We don't know for sure. We haven't explored it entirely, but it seems to be working. Let's take and crank the width down to 3 digits. Let's change the initial value from 1549 to width of 3. So if this thing works, we should end up with a Kaprekar's constant for values that are 3 digits wide. And we do. The Kaprekar's constant for 3 digits happens to be 495. When we start looking at these things, when we start thinking about these things, when we start running all 10,000 values through classic Kaprekar's constant or Kaprekar's computation, we can draw a schematic of those values, of those operations, of the way things work. And the idea for a schematic comes from this book. I will put a link to it in the comments. Also in the comments will be the GitHub for all of the code that I'm demonstrating, for all of the algorithmic things, for the images. It should be there, ready, standalone, ready for you to use. Let's take a look at the schematics. This is a schematic for 6174. Let's see if we can come back in here. We started off with 1549. When that was sorted, it became 9541 and 8082. My claim is that this value, 8082, when it is sorted high to low, will be in this schematic someplace. And it is, in fact, right here. The value, the sorted value after 8820 is 8532. That goes to 617 or 7641, sorted low to high, skewed high to low, and thereafter you're stuck. How we got to this 8820 is based on this number down here, this subtraction down here. But how we got to here is not on this scheme. So there are some number of subtractions here that will end up with these ordered digits 8820. One example of that would be, well, I'm not going to go diving down that rabbit hole. The way to read this schematic is with the black lines. That is part of the operations. That is part of Kaprekar's constant. That is part of the computations. The red is a loop, a cycle. So this is, in graph theory terms, this is a digraph. This is a directed graph where the edges show the operations and the red is the cycle. And this is fairly straightforward for 4-digit Kaprekar constant. We'll skip that one for just a moment. This is the one for 3 digits. This corresponds to this. So we have this first value, 891. We sort that from high to low, and we get 981, followed by 972, followed by 963, followed by 954. And after that, we're stuck. So Kaprekar's constant for 3 digits is 495. In a diagrammatic form, it is this value right here. Let's try this for 2-digit wide numbers. Main, and the first value is the initial. Let's do 49. But they're only 2-digit wide. So we're talking about numbers between 0 and 100. Actually, when you start taking out the, or when you apply the 2-digit restriction, it goes from 1 to 98. But let's take a look at this. We start off with 49, and they're 2-digit wide. And we end up with this. From a schematic point of view, it is this thing. You notice there's no black arcs. There are none. After the first operation, right here, which was a 54, followed by a 90, followed by an 81, followed by a 63, followed by 72, and back again. After the first operation, you're in a cycle. So the lead up to this cycle is 1. There's only one operation, and then the cycle itself is 1, 2, 3, 4, 5 operations long. And this, the cycle could be 1, 2, 3, 4, 5, 6, and then you are into here. So the head, the precursor to the cycle is 6, and the cycle itself is 1. If we go a little further, this is 2, this is 3, this is 4, our friend. What would happen if we tried 5? Go back here, our friend 49, let's make this 5. So we're looking at digits or values that are 5 digits wide. So it would be like from 0 to, what is that, 5? 10,000. So we have this number repeating. So our cycle is 1, 2, 3, 4, and it took a couple iterations to get there. This is our schematic for 4. This is our schematic for 5. Notice that there are 4 different cycles. There's a cycle between these two values. There's a cycle here, so I guess it's actually 3 cycles. Once you get into one of these cycles, you don't get out. Which cycle do you get into? It depends on your initial value. And this is kind of fun. This is kind of interesting. Getting back to knobs. One of the knobs is base or a width of 4. We've now explored that area some. We know that for a width of 4, we end up at 6174 as the value. For a width of 3, we end up at 495. For a width of 2, we don't end up at any particular value. We cycle through several of them all the time. For a width of 5, we have 3 different cycles depending on which number you start with. So it is a little strange. But inherent in all of this is the idea of a decimal numbering system, because this is 6174, that is decimal, because we think in decimal all the time. So the base that the numeric operations are in is another knob that we can twist. So let's see what happens, how we attack that. This is numeric widths. This is, okay, this is the width. Let's just hold off at that for just a second. And let's, okay, let's get back to the wheres. This is the width, and now we are interested in how many subtractions to get to that repeat value, and then how many subtractions in the cycle. So we're looking at how big is this thing right here, how many operations are in that cycle, and how many operations does it take me to get to the cycle. So if we were following just this single chain of operations right here, we would have subtraction, 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 subtraction. Oops, we have detected a cycle, and that cycle has 4 subtractions in it. So we're interested in the number of subtractions to reach the value the first time, and then how many subtractions does it take to get there the second time. And that's what we're going to do here. Our get digits and order digits are the same. Our subtractions are the same. We are doing this for whatever width we are interested in. And then we start looking at this part. Where is that first value? So that is where that repeat number first occurs. And then how big is the cycle? And that is this part. So let's go through all this. Our width, our favorite 1549 width of 4. So now we have the routine telling us explicitly that the cycle starts at 3 and is 1 operations long. If we do initial value of 2, width of 2, it starts at 2 and is 5 operations long. So the number of operations changes based on width, based on initial value. The number of operations in the cycle changes based on the width, perhaps. How do we do that? You know, we're starting to get an idea of a graph. We're starting to get the idea that if we start at one point and we go to the next one and then the next one, we end up in this loop somehow, this idea, this construct, this constraint. Let's get back to our knobs. We have the knobs for decimals. We now can visualize graphs, which feeds into our ideas of these types of structures. Let's get down into different bases. So in this one, we have the width, our friend. We have an initial number that we beat up on quite a bit. And we have this idea of a base. If you are a computer science kind of person, if that is your training or avocation, then you are familiar with decimal. You are familiar with hexadecimal. You are familiar with binary. You may be familiar with octal. So you've got 4 different bases that you are conversant in. Conversant to the point where you might use a calculator to change from one base to another, but the idea of different bases is something that is part of your training, your profession, your life. Let's see what happens with Kaprekar's constant when we start looking at different bases. We are now going to import this file called baseslibrary.r. We'll take a quick look at that. We won't dive into it. This is the source of the routines in this library. In sort of 30 words or less, so it's going to be more. Glyphs are the things that get printed to the screen. In this case, there are 36 different glyphs, starting with the first digits 0 through 9, followed by uppercase A through uppercase Z. So those are the things that get printed to the screen. This is a function that will convert a base, convert a number to a base. It's got some neat stuff in it. If you want a full explanation, I encourage you to take a look there. This format is a way to do a pretty print of a numeric value. If you are an advanced R programmer, then you will understand the relationship between the highlighted dot base and, where'd it go? This class equals base. If you're not an advanced programmer, just accept that it works. This is how we print things out. This is how we do operations. And this is how we do mathematical stuff. The rest of this is a little bookkeeping. So, at a 50,000 foot view, we take in three values, a number, the width of that number, and the base of that number. Decimal, octal, hexadecimal, binary, whatever it happens to be. We sort and subtract, and we check to see if it's in the list of previous values, and then we print out some routines. So let's do our favorite 5149. 5149 base 10. So we're evaluating 1549 base 10, gets through there, and we return the same values. We are sort of confident that that works. Let's do the same thing, only we're going to change the base. We're going to make the base be 16. So we're now doing hexadecimal. (1549) base 16. Do the subtraction. Notice how there's a difference now. This was 8082. This is 80E8. It's a different value because each one of these digits is a different base. Sort, subtract, sort, subtract, sort, subtract, keep on going. In this case, cycle starts at 6 and a 6 operation. So we've got 7FF8, and here we have 7FF8 a second time. Once we detect that same value, we know we're in a cycle, and it's going to stay there forever. So Kaprekar's constant probably works for different bases. We're fairly confident that it works for base 10. Our code, our routine detects the cycle for base 16. We're starting to get some confidence. And finally, we'll just run 1549 at base 23, because 23 is a nice round number. And here it is. Here is right there and right there. Initial testing seems to indicate that Kaprekar's routine works for different bases as well. So we've identified yet another knob that we can twist on Kaprekar's routine. Things that pop up. But now that we have gone through that, we can start talking some more about how to search for these different values. That leads us into this idea of splitting and sorting the digits. with Kaprekar's routine, Kaprekar's constant, we just did that blindly because that's what the algorithm says to do. If we look at what that means, we have things like 1234 and 1243 as example values. If we split those, sort them, then they both become 4321. So do we really need to evaluate 1234 and 1243? Or can we just somehow identify the unique values, 4321, and just do those? Can we do that? And if so, how would we do it? What would be the effect of doing that? And this is a little algorithm to do that. We take our width and our base, because those are important. And then we count up the number of digits. We create the values. So we're going from 1 to the maximum value minus 1. We create a temporary value with all sorts of leading zeros as necessary to make sure that it is the correct width wide. We split them up into individual values. And then we sort those digits. We find the unique values of those digits, and we find how many values there are. So line 7, if we said base 10 and the values were 1111, then line 7 would look at those digits, those unique digits, and say you've only got one digit there, therefore you that's not a valid Kaprekar's constant, so I'm going to ignore it. Otherwise, I'm going to write the value out to a file. So this would be this would be sorted, written out to a file. This would be sorted, written out to a file. So we have two entries that are the same in the file. And then we use the operating system to sort the contents of that file and then to return the unique strings. So while 4321 was written out to the file twice because we were processing the numbers, after we were finished, 4321 would only exist one time in that file. So we are reducing the number of values that we have to evaluate. And that's what this little routine does. It says, I'm going to look at all values that are of some width, and I'm just going to get the unique digits out of them, sort them, and put them back into a value, and write that string out to a temporary file. I'm going to sort and unique that string or that file, and then give you some statistics on how things work. So if we run this for 3, that should tell us the number of unique values based on Kaprekar's constraints that are 3 digits wide. And there are 220 of them, vice 1000. So we have reduced our Kaprekar exploration space by 78%. If we do that for 3, 4, 5, and 6, we would end up with 220, which is what we have right here. 715, 2002, 5000, and 5. So let's just go ahead and run this quickly. So for width of 3, we reduced our exploration space by 78%. For 4, it's 92%, 93%. For 5, it's 98%. So we have reduced the amount of computations by 98%. It does take time to do this reduction, yes, but the computations afterwards have been reduced, and it is still cranking away on the 6th. Remember, we are exploring this world of Kaprekar's constants. We have looked at 2's, widths of 2, 3, 4, glanced at 5, but that knob we could continue to twist and keep it going. So for a width of 6, instead of 1,000,000 values, all we have to do is process 5,005 of them. When we do that, we end up with a plot that looks like this. This is nice and linear for 3, 4, 5, and 6. Just a nice straight line there on a logarithmic scale. So if we were to plot this on a linear scale, it would have a very steep knee, a very pronounced knee. We're getting into big data areas, big data problems. This is linear. If we do it, this is log plot. So once we start getting into big data problems, we saw how long it took to compute those to clean up those 5 million, those 1 million values down to 5,000. What happens when we go to a width of 7, a width of 8? These are starting to get into big data problems, big data areas. The simplest way, or if you look at the computations for each one of these schematic values, if I start off with a chain that goes through here, through these guys, it is totally independent of this chain until we get to here. Totally independent. So these operations are not dependent at all on these operations. That kind of problem cries out for parallel processing. And that's what we're going to do. This is our studio using these files. You notice how this is red here, where the others are black. That means that this file has been modified. All of these files are going to be on GitHub. You'll be able to download them. They should run without any problems, with the exception of this parallel processing file. on this machine, I have downloaded GitHub to this directory, and under that, GitHub put things here. Oops, missing a slash there. This line and where'd it go? This line are the ones that you'll have to change to have this run on your local machine. And what you'll have to do is put the full path name, not a relative path name, but a full path name. So let's see what we can do for doing this work in parallel. What kind of algorithm would we have to do? Okay, this is the routine to recreate the strings that led to things like this 5,005. How do you get those 5,000? How do you recreate the values that got to 5,005? This is the parallel computation part. It has 3 arguments. The width, our friend width, that we have used extensively. The base, which we have used to a lesser degree, but we understand now. And cores. Almost all modern CPUs have some number of cores inside the CPU chip itself. The number of cores varies. If you have really old technology, you only have 2 cores. If you have modern non-server technology, you might have 8 or 16 cores. This is not GPU, this is CPU cores. So the argument is, how many CPU or how many cores do you want the routine to use? We have the values that we're going to process. Those are either the in the 1,000 values, if we're, well, let's not do that one. The 100,000 values, if we are using a width of 5, or the 2002 values that are unique for a width of 5. So either all the values being processed or a subset of all values. Those values are spread across however many cores you want to be used. We have to configure the cores as a computing cluster. R by itself, by default, is a single thread, single core operation. So we have to configure it specially to handle or to operate as a computer cluster or a computing cluster. And then for however many cores there are, distribute the values, get them running, and then go on to the next one. So we start spreading the workload across all of the cores. So now we have this controlling process that we have on the screen right now. It has kicked off individual processes across all cores. When it's finished, we've got to get the answers back, so we have to reassemble things and return it. And that's what's happening in here. You notice there's a fair amount of code here. So if we don't tell the machine or don't tell the software how many cores to use, it will use all cores that are available. This is kind of an interesting problem in that different operating systems report cores differently. On this machine, I am running an AMD 8-core chip. The operating system will say that there are 16 cores because of the way it counts threads on a core. Windows works differently. So our friend, the width that we are used to, and unique values only, that is getting to these 5005, 2002, and so on. Some words about what's happening. And then we're going to start timing things. This is the amount of time it takes to process the data, to go down to the width of 3 and either return 1,000 values or 220 values. So there is a time processing, and then we report that. We make a cluster with the number of cores. We spread the work out across those cores. That's what's happening all inside of here. We stop the cluster and we report what we did. The work is actually done in this function, which is all the way back up here. It brings in this library file, our friend get digits, sort digits, the width, the results. It parses up these numbers of interest, either the 2002 or the 100,000, however many we have, and then goes through and starts evaluating them. So there's a fair amount of code that's in here. It will also create a graph viz file. Graph viz is the file that generates pictures like this. You may or may not want that. So that is basically what it does and how it works. Let's go back up here. Notice how our function section over here has changed quite a bit. There's more stuff here. So we will take our friend with the 4. We will use all possible cores, and we will use unique values only. So that will be the 2002 out of 100,000 or 10,000. Excuse me. And it took approximately 2 seconds to process the data, and then 0.2 of a second to, 2 seconds to prepare the data, and 0.2 of a second to process the data. If we change this to false, so that it will process all 10,000 values. Before we do that, this is 705 because the repeating digit values were eliminated. So it took 1.9 seconds and 0.2 of a second, which is okay. When we start getting into, let's run this with 1 core. So this is simulating going through and processing all 10,000 values on a single core. The processing time should be still about 1.9 seconds. Excuse me, the preparation time should be about 1.9 seconds. The processing time should be considerably larger. With 16 cores, it took 7/10 of a second. With one core, it took 3/10 of a second. The reduction in preparation time was probably because it didn't have to do any looping. In theory, we could continue to increase the width, run as many cores as possible, and process only the unique values to reduce the processing load. So preparation time would gradually increase, and hopefully that increase would allow a significant reduction in processing time. There, in this routine or this report, I talk about the performance on my computer system using parallel processing to go for more width. I was successful in running 2, 3, 4. These are widths. 2, 3, 4, 5, 6, 7. I terminated trying to run 8 because I let this hardware setup run for a couple days and it hadn't finished, and I wanted to use my machine for other things. From an algorithmic point of view, exploring Kaprekar's constants is on the order of big O base n, base raised to the n, meaning that the number of operations will increase exponentially based on the width of the values that we're trying to put in. So it has an exponential curve. Practically, we can work on small values of width, 2, 3, 4, 5, 6. Large values of width, 12, 1500, maybe beyond our capacity to process right now. Exploring Kaprekar's constant has been a delight. It is deceptively simple. The original algorithm, the classic algorithm, has only got 4 lines. That's all. That's all there is there. The practical implementation, once you start tweaking the knob to start looking at performance of how Kaprekar's constants, if they exist for other widths, is fun. Figuring out how to minimize computational load by finding unique digits, unique string combinations, is fun. Figuring out how to process larger values of n, as far as I was able to get, becomes a big data problem. Wandering through Kaprekar's constant, wandering through this realm, has been an absolute delight. It is one of the few algorithms that I have bumped into that I will say that about. The implementation, I did it in R because that was convenient. Could it be done in any other language? Absolutely. There's The only part that might be a little tricky might be to do the parallelization. Some languages support that better than others, but there's nothing inherently R-ish in these routines. I enjoy playing with it. I enjoy going and impressing my friends and confounding my enemies by predicting 6174 and winning an adult beverage or two from it. Anyway, there's a couple other routines, a couple other problems that I am playing with that when I solve them to my satisfaction, I will include them in this library. Hope you have a good day and be kind to others. Hope to talk to you soon.